Have you ever really thought about what gives a lemon that sharp, puckering taste? Or why soap feels so slippery between your fingers? Well, the answer is this incredible hidden chemical language that's being spoken all around us and even inside our own bodies. So today, we're going to learn the basics of that language: acids, bases, and salts.
Okay, I know what you're thinking. This looks like a totally random list, right? A sour fruit, a bar of soap, and something for heartburn. But believe it or not, they are all part of the exact same fascinating chemical family, and you're about to find out exactly how they're all connected.
So let's start with the absolute basics, stuff you can literally taste and feel. Acids. Well, acids are the things that taste sour. Think about that sharp bite from a lemon or the tang of vinegar. Bases, on the other hand, usually taste bitter and feel really slippery when you touch them. You know that smooth, slick feeling of wet soap? Yeah, that is a classic property of a base.
But what's actually happening on a chemical level? What really makes something an acid? It all comes down to one tiny little thing: the hydrogen ion, or H+. When you put an acid in water, it basically releases these hydrogen ions. The more H+ ions it lets loose, the more acidic that solution becomes. Simple as that.
And you can find these acid-producing substances literally everywhere. The citric acid in your lemon juice, the acetic acid that makes vinegar, even the lactic acid in curd. Heck, your own stomach produces super powerful hydrochloric acid to break down your food.
Now, for the other side of the coin, a base. It does something really similar, but instead of releasing hydrogen ions, a base produces hydroxide ions. That's OH negative, when you dissolve it in water. So you can think of the hydroxide ion as the chemical signature of a base.
And just like acids, bases are all over the place. We've already talked about soap, right? But things like baking soda, lime water, and yep, those antacid tablets you take for indigestion, all of them are common bases, just working their chemical magic in our daily lives.
Okay, here's a quick little clarification that's going to come in handy. You might hear the word alkali thrown around. An alkali is just a special name for a base that can dissolve in water. So here's the key takeaway. All alkalis are part of the base family, but not all bases get to be called alkalis, only the ones that dissolve.
Now, this is super important. A lot of people mix this up, thinking strong acid means super dangerous. In chemistry, strong and weak are all about how they behave. A strong acid, like hydrochloric acid, completely ionizes in water. It releases all of its hydrogen ions. A weak acid, like the one in vinegar, is a little more shy. It only releases a few. That's the only difference. Strength is not the same as danger.
So what happens when these two opposites finally meet? Well, it's this amazing chemical reaction called neutralization. It's really simple. When you mix an acid and a base, they react and create two totally new, stable things: a salt and good old water.
But sometimes that neutralization reaction is a little more dramatic, like when an acid meets a special kind of base called a metal carbonate. Think vinegar meets baking soda. You get that awesome fizz. Those bubbles you see are actually carbon dioxide gas, and it's the very same reaction that makes those classic school project volcanoes erupt.
All right, so how do we measure all this stuff? We use something called the pH scale. It goes from 0 to 14, and the rules are super easy to remember. First up, anything with a pH that is less than 7 is an acid.
Dead center. At exactly 7, we have our neutral point. This just means a substance isn't acidic or basic, and the perfect example of this is pure water.
And finally, you guessed it, any substance with a pH greater than 7 is a base, which we also call alkaline. The higher that number climbs above 7, the more basic it is. Now, this scale makes a whole lot more sense when you see it with real-world stuff. So lemon juice is super acidic, way down around a pH of 2. Pure water is sitting right there in the middle at a perfect neutral 7. Soap is basic, floating around a 10, and something powerful like household bleach is a really strong base, all the way up at 13.
Okay, so that's the science part. But why does any of this actually matter to you? This is where it gets really, really cool, because these chemical principles are working all around you, all the time, in ways that are probably going to surprise you.
Let's just take baking soda for a second. It's technically a salt that acts like a weak base, and it is a total workhorse. In baking, it reacts with acidic stuff to release carbon dioxide gas, which is what makes your cakes light and fluffy. If you've got indigestion, it neutralizes that extra stomach acid. It's even used in some fire extinguishers. How about your teeth?
Well, after you eat, the bacteria in your mouth produce acids as they break down sugars. And if the pH in your mouth drops below 5.5, your tooth enamel literally starts to dissolve. So what do? We brush with toothpaste, which is a base. It performs a tiny neutralization reaction in your mouth every single day to save your teeth.
The chemistry of salts also helps us build things and heal injuries. Think about plaster of Paris, the stuff used for casts. It all starts out as a mineral salt called gypsum. When you heat gypsum up just right, it loses some of its water molecules and transforms into that familiar fine white powder.
And here's where the magic happens. When you reverse the process, you just add water back to that plaster of Paris powder. It immediately starts to reabsorb the water, turning itself back into gypsum and setting into a hard, solid mass. It's perfect for keeping a broken bone in place.
Now, because these substances are so reactive, you have to be careful. A few key safety rules to always remember. Always, always add acid to water, never the other way around, because it can create a dangerous splash. Never taste or smell chemicals you don't know, and protect yourself. Use gloves and goggles when you need to.
So at the end of the day, I want you to remember this. This isn't just something you learn about in a chemistry lab. Acids, bases, and salts are running your kitchen, your body, the soil in your garden, your teeth, and even our planet's rivers. They're everywhere. Now that you know, what are you going to notice differently today?